Hello and welcome to session 7 of the Arista TAC Webinar Series 2023. We took a short break and we're back. And so we are here with a 3-part session covering EVPN. We're super thankful to see all of you on here today because, well, if you weren't here, we wouldn't be doing this. So thanks for those of you that are joining us for the first time, and thank you to all our customers who are coming here after attending the previous sessions. We're super thankful for you being here, and we hope you enjoy the session. Today is going to be part 1 of our EVPN portion, where we are going to focus on debugging traffic flows in an EVPN-VxLAN environment. I'm Divya Wagner. I lead the technical services team in the Americas. And joining me is Neetu Dubey, our team lead, who is going to walk us through today's session on EVPN. Also, we have a panel. So if you have any questions during the course of this session, feel free to just type it into Q&A. Our panel is live and they will make sure that we answer as many questions as we can, throughout the duration of this session. Also, while we go through the training session today, we are going to be using very specific problem descriptions and topology. What sets this webinar apart from all other webinars is that we actually take examples or situations that we see in our day-to-day that occurs in networks. We kind of use that as the basis for explaining how to troubleshoot it. So, some of it might be very close to what you have in the network. Some of it might be relatable, but we hope that at the end of this, it's a practical experience and you learn, with an actual network topology, how all of that works. Now, a topology was sent out to all of your emails. If you registered, right, it was sent out on August 22nd. I would strongly recommend that you download it because that will be very useful for you to follow along throughout the session today. And if you don't have it, you don't have to go and search frantically in your email. You can just check out the chat session, and our panelists have put in the links where you can download the topology, and we can use that as we go through this. Also, I mentioned the Q&A, and in the chat session, we will continue to put any relevant information while we're talking about it, like we're sharing email addresses or any useful links, or looking for feedback. We'll continue to post that in the chat session as we go through today. And for those of you that are joining us for the first time, or those that need a refresher, just a quick note, moving on to the next slide, that this year we covered a range of topics, right? So we've covered layer 2 debugging, layer 3 debugging, and VxLAN. And even prior to 2023, when we started in 22, we also covered EOS health checks and so on. The good news is all of these sessions are recorded. They're all made available to you. So if you either go to our Arista community page for TAC webinars, or you go to our Arista community channel on YouTube, you will be able to view any of the previous recordings at any time that you want. Feel free to share it with your teammates or anyone else that you feel will find it useful. And also, any material that we use during the course of our webinars, including the slide deck that's being used today, the topology, the Q&A at the end of this session, all of that will also be made available to you. You can download it at the end of this session on the Arista Community Central page. Okay. And with that, I also want to take a moment to quickly introduce the custom TAC training that is offered by Arista TAC. So if you're looking for sessions, and we've sent this out in a feedback form, a lot of you have given us some very positive feedback on this and expressed your interest. Whether you're a large organization with a global operations team or a small, lean, mean operations team, I think this would be extremely useful. What we do in these trainings is we cater it specifically to the platforms that you have in your network, the features that you have in your network. And if you're a customer that has open cases with us, it will also include a comprehensive analysis of all of those cases. So when we deliver this training, it's very specifically troubleshooting based on what you have in your network that would be extremely useful to your operations teams. We have thus far delivered some of these to our Cloud Titans and our enterprise customers, and have received great feedback. It is a paid offering, and if you are interested in learning more about this for your network and for your company, please contact us at tac-custom-training@arista.com. Also, if you are just looking for more general training on Arista products or the ACE certification, which is the Arista Certified Engineer certifications, you can contact our training team at training@arista. Now, as we go through this session, also, like I mentioned, we will be dropping in the feedback form and in the chat session and any other relevant emails. So you have all of this. We will recap it at the end. You don't need to jot anything down. And as I mentioned earlier, all of the information that we're presenting today will be made available to you. Without further ado, I'm going to hand it off to Meetu to take us through EVPN troubleshooting. Thank you.
Thank you, Divya. Hello, everyone. Good morning, good afternoon, and good evening. My name is Meetu Dubey, and I'm part of the Arista TAC team. For today's session, we'll be taking a look at some common problems in the EVPN-VxLAN environment. We'll be using the outputs in CLI to trace the path of the traffic and get an understanding of possible issues in control plane learning through BGP EVPN and data plane forwarding through VxLAN. Before we take a look at the topology, let's talk about a few elements that bring together an EVPN-VxLAN environment. EVPN utilizes multi-protocol BGP to advertise control plane information that is needed for packet forwarding within VxLAN. This control plane information includes MAC address reachability, ARP entries, flood lists, and IP prefixes. The control plane information is advertised using a BGP EVPN update packet that can be identified using the address family identifier, which tells us the type of routes being exchanged, and the subsequent address family identifier, which has the value of 70 for EVPN. While the control plane is taken care of by BGP EVPN, on the data plane side, we have the network virtualization overlay, which is the overlay network that provides layer 2 and layer 3 VPN services to the end customers or tenants. The NVO that we have here is a VxLAN fabric, and an alternate to that would be MPLS. Within the NVO, we have NVEs, or the network virtualization endpoints, that are responsible to encapsulate the traffic into the overlay network. The NVE here is a VTEP. Between the NVEs or the VTEPs is where we have the EVPN instance running that visualizes the entire network as a single logical switch that maintains the control plane information for the end customers or tenants. For each tenant, we define a MAC VRF on the VTEP or the network virtualization endpoint that stores the MAC address table for the specific customer or tenant. Within the MAC VRF, we would define the route distinguisher, which uniquely identifies the entry for a specific customer on the VTEP. And we also define route targets in export and import statement to export and import the control plane information across the VTEPs. Here is an example of a BGP EVPN update packet that is advertising the reachability of a MAC address. We can see that the route distinguisher is part of the NLRI, and the route target is part of the extended communities. This route target value would be used by the receiving VTEP or NVE to import the MAC address into the correct MAC VRF. The way the VLANs are mapped to the MAC VRF defines the EVPN service model in use. In today's problem descriptions, we'll be taking a look at VLAN-based and VLAN-aware bundle, where in VLAN-based, we have one VLAN mapped to one MAC VRF. And in a VLAN-aware bundle, we have multiple VLANs part of a single MAC VRF, such that the VLAN tag needs to be carried in the BGP EVPN update packet. We talked about the different control plane information that is needed for packet forwarding within VxLAN. This is classified as different EVPN route types. And today we'll be taking a look at type 2 MAC IP route that advertises the reachability of MAC address and optionally ARP. We'll also take a look at type 3 inclusive multicast route that is used to discover the remote VTEPs in a VxLAN fabric, and it helps the VTEP populate its flood list based on the VNI. Here is the topology that we'll be using today, and you can find this in the chat section of the webinar as well. This is a EVPN-VxLAN environment where we have 3 bridging VTEPs, VTEP 1A, 1B, VTEP 2A, 2B, and VTEP 3. The VTEP IPs are represented by loopback 1, and we also have a loopback 0 that is defined on each physical device. That is a unique IP on which BGP EVPN peering would be formed. This is represented in blue, and this is where the control plane information would be advertised to the remote VTEPs. Other than the BGP EVPN peering, we also have BGP running on the links between the VTEPs and the spines. This is represented in the green dots. This provides the underlay connectivity to the loopback 0 and loopback 1 IPs of the network. For the devices, we are using different data center switches for both VTEPs and spines, but all the devices are running the EOS version 4.29.4m. We'll have different host connections, host IPs and VLAN configuration, and even different EVPN service models in each problem statement. So with that, let's go ahead with our first problem statement. This is again a bridging environment where we have VLANs part of different VLAN-aware bundles, tenant A and tenant B. And the customer has reported that certain hosts within VLAN 27 are not reachable. The setup was working fine until some time back, and now the issue is seen only for VLAN 27. We also have VLAN 11, which is part of the same tenant A that is not facing the issue. We also have a sample flow from host 1 to host 3 that does not seem to be working fine for VLAN 27. With this information at hand, let's go ahead and take a look at the sample flow. From host 1, we initiate a ping towards host 3, and we see a complete packet loss. Taking a look at the ARP entry for host 3, we see that the ARP is resolved. Checking the same for host 1, we see the ARP is resolved as well. As there are hosts behind different VTEPs, it would be a good test to ping the different IPs and see if there are any commonalities in terms of source IP or destination IP not being reachable, or traffic that is sourced from a specific VTEP or destined to a specific VTEP. We see that host 1 can reach host 2, but host 4 fails. Note that both host 3 and host 4 are behind the same VTEP, VTEP 3. From host 2 as well, dot 3 and dot 4 have complete packet loss. It would be good to quickly check if host 3 is able to ping host 4. If not, then the problem would be localized to a single switch. In this case, when we ping dot 4, we can see that the ping is working fine. With these tests done, let's go back to our sample flow from host 1 towards host 3. We will run a continuous ping and trace the path of the traffic from VTEP 1 towards VTEP 3. Taking a look at VTEP 1A and 1B, when we run the command show MAC address table for VLAN 27, we see that host 1's MAC address is learned locally on port channel 1. We would expect the same output to be present on VTEP 1B as well, as both 1A and 1B are part of the same MLAG domain. Note that we are not learning the MAC address of host 3 on VX1. Let's go ahead and check if VTEP 3 is learning the MAC address ending in 4A89, that is host 1. We only see entries that are local to VTEP 3. Now, it is important to understand that when a VTEP or a device learns a MAC address locally, in BGP EVPN, it is going to advertise this as a MAC IP route. As VTEP 1A and 1B has learned 4A89 MAC address, let's see if VTEP 3 is receiving this as a MAC IP route. The command here is show BGP EVPN route type, and we specify MAC IP with the specific MAC address. We see routes received for both VNI 11 and VNI 27. Now, a device can have potentially different sources of MAC learning. It can learn a MAC address locally or via static entry through CLI, or even through protocols such as .1x, or in our case, BGP EVPN. With such different sources of MAC learning, the device maintains an L2RIB table to which it inputs or imports these entries. And then based on factors such as preference, where a static entry would have a higher preference, and MAC moves, that is tracked by sequence numbers, it is going to generate an L2RIB output table. This would eventually reflect in the show MAC address table command output. Let's see if VTEP3 has imported these entries into its L2RIB input table. The command here would be show L2RIB input. We specify BGP and the MAC ending in 4A89. We do see an entry, but for VLAN 11, that is learned behind VTEP1. We would expect this output to reflect in the show MAC address table output for VLAN 11. And indeed, we see this learned on VX1. However, we are not importing any MAC IP routes for VLAN 27. At this point, it would be good to check if the route target of the received routes has the same value as that configured in the import statement of VTEP3. To do so, we will run the command show BGP EVPN route type MAC IP, and we will filter with the MAC and the VNI 27 and add the keyword detail. We can see that for all the NLRIs, we have the same route target, 1010-1010. We can either compare this with the running configuration on VTEP3 or run the command show BGP EVPN instance. We do see that tenant A, which has VLAN 27 mapped to it, has the correct route target import statement. Still, we are not importing this into the L2RIB. Next, we also saw that VTEP3 was learning MAC addresses locally. This is true for both VLAN 11 and VLAN 27. Let's go ahead and check if VTEP3 is at least generating the MAC IP routes for VNI 27. The command here remains the same, where we check route type MAC IP and we filter it with VNI 27. We only see routes that are received from remote VTEP, VTEP1A and 1B. Comparing this with the working VLAN and VNI 11, we see that the MAC IP route is generated for the locally learned entry. Now, even though the VTEPs are not learning the remote MAC addresses in their MAC address table, we know that a device is going to flood the traffic to all the ports in its VLAN if as unknown unicast traffic. Let's check if VTEP1A is flooding the traffic to all the ports. As VTEP1A is in VxLAN fabric, we'll go ahead and take a look at the flood list. The command show VxLAN flood VTEP VLAN 27 tells us that the only flood list we have is VTEP2. Now we know that in BGP EVPN, the flood list is populated based on the IMET routes. Let's see if VTEP1A is receiving this IMET route for the VNI 27. We see entries only present for VTEP2A and 2B. It would be good to check if VTEP3 is even generating the IMET routes in the first place. Running the same command, we see entries that are received from remote VTEPs, VTEP1A, 1B, and 2A, 2B. We would expect that these IMET routes are installed in the flood list table of VTEP3. Let's go ahead and check the command show VxLAN flood VTEP for VLAN 27. We see that the output is empty. Now, just like the MAC IP routes get imported into the L2RIB, the L2RIB also imports the flood sets from different sources, such as CLI, and in this case, BGP EVPN. Let's check if the show L2RIB input command reflects any flood set for VLAN 27. We can see that the output of this command is empty. At this point, we can say that VTEP3 is receiving both IMET routes and MAC IP routes, but it is not installing it in its L2RIB table which would eventually reflect in the MAC address table or flood list table. This is represented by the green line in the diagram. VTIP3 is also not generating the IMET routes or the MAC IP routes from the locally learned MAC addresses in VLAN 27. As the issue is specific to VLAN 27 only, it would be worth checking the configuration of the VLAN aware bundle tenant A. Taking a look, we see that tenant A has VLAN 27 mapped to it. But also note that VLAN 27 is configured as part of tenant B. This is a misconfiguration, as the same VLAN cannot be part of two VLAN aware bundles. There are different ways to identify this misconfiguration. Whenever a VLAN is configured as part of two MAC VRFs, a syslog gets generated on the device. This can be seen in show logging, and this happens as soon as a configuration change is made. We do see a MAC VRF conflict log that is generated, and we'll take a note of the timestamp as well to see if any config change was made around the same time. But before that, we know that VTIP3 is running the EOS version 4.29.4m. Starting the EOS version 4.29.1f, we have the command show BGP EVPN sanity and the detailed version of the command that can give us any EVPN misconfiguration or attributes that might be inconsistent. This may or may not cause traffic to fail or control plane to fail, but this command is really helpful in identifying such inconsistencies. We can see that the L2 category is marked as fail, and the system is identifying that the MAC VRF has overlapping VLANs. Let's go ahead and check if any configuration change was made around the time the syslog was generated. The command that we use here is show AAA accounting logs. Scrolling back up, we can see that tenant B was edited and a subset of VLANs was added to it. Comparing this with what we have in our topology, we can see that VLAN 1 and 27 are not supposed to be part of tenant B. There are a few other VLANs that have been configured, but let's go ahead and check what is the current running configuration under tenant B and rectify if there are any errors. We drop into the router BGP mode and into the specific VLAN aware bundle. It is important to note that all VTIPs should have the same mapping of VLANs to the MAC VRFs. This would ensure that the control plane information is learned correctly. We know that we need to remove VLAN 27 and VLAN 1, but also note that VLAN 127 is missing from the configuration. We'll go ahead and make the necessary changes. The command here would be VLAN remove and VLAN add to edit the current list of VLANs. Before we go ahead and take a look at our pings, let's verify if the errors have been resolved on VTIP3. Running the command show BGP EVPN sanity again, we see that the command output is clear. Let's also verify the running configuration on both tenant A and tenant B to make sure that all VLANs are mapped correctly. Indeed, the configuration seems to look fine. We see that our ping has already recovered. This would have happened as soon as we removed the VLAN 27 from tenant B. Let's also go ahead and ping .4 from both host 1 and host 2. We can see that this has recovered. To summarize, with VLAN 27 being part of two MAC VRFs, VTIP3 was not able to install the IMET routes and MAC IP routes in its flood list or the MAC address table. It was also not able to generate the routes that would eventually get advertised to the remote VTIPs. Also note that at the start of the troubleshooting, host 1 had host 3's ARP resolved. This is possible if the traffic was working fine until some point, and after the configuration change, the ARP did not time out. Also note that VLAN 127 was missing from the VLAN aware bundle tenant B, which would potentially impact all the traffic towards VLAN 127 on hosts behind VTEP3. In terms of the commands, we particularly focused on show BGP EVPN route type MAC IP and IMET to see the routes that are received and generated. We also focused on the show L2RIB input BGP command to see if the MAC addresses and the flood sets were getting imported. But the command show BGP EVPN sanity detail was particularly helpful to confirm the misconfiguration of VLAN 27 in 2 MAC VRFs. With this, let's go ahead and take a look at our problem statement 2. We again have an EVPN-VxLAN bridging setup, and we have one VLAN 10 that is mapped to a MAC VRF. Note that in this topology, host 2 and host 4 are behind VTEP2A and 2B. And the customer has reported that during a planned maintenance window, certain flows behind VTEP2A and 2B were not working fine. The maintenance window involved bringing down the links from the spines towards VTEP2A. And a similar maintenance activity was performed on VTEP1A few days back, and it worked completely fine. The impact is definitely not expected, given that most VTEPs have device redundancy in terms of MLAG and link redundancy in terms of having multiple links to the spines. We do have sample flows that are impacted and non-impacted. With this information at hand, let's go ahead and take a look at the maintenance window. From host 1, we will first ping host 2 and host 4. We see a complete packet loss towards 10.2. And if we check 10.4, it seems to be working fine. We can also verify the ARP entry for host 2. The ARP entry for 10.2 seems to be complete. Let's also verify the sample flows from host 3 towards host 2 and host 4. Ping to 10.2 in this case works fine, but to 10.4 fails completely. Let's take one of the destination IPs. Let's consider host 2 here. We know that there is one flow that is working fine towards host 2 and the other that is not. With this information, it would be good to take a packet capture on host 2 and see what type of traffic it is receiving in case of complete loss. We do see that the ICMP echo requests from host 1 are received, and host 2 is also generating the ICMP echo replies. This is a good test to perform as it gives us a head start in troubleshooting. We know that the forward traffic flow from host 1 to host 2 is working fine for now. We will now focus on the ICMP echo replies from host 2 towards VTEP2A and 2B and to the remote VTEP1A and 1B. We have a continuous ping running from host 1 to ensure that the ICMP echo replies are generated continuously. Let's take a look at VTEP2. We see that host 2's MAC address is learned on port channel 1 on VTEP2A. A similar output is seen on VTEP2B. However, to determine which device is actually receiving the ICMP echo replies, we have configured a monitor session on VTEP2A. This monitor session is in the receive direction of port channel 1. So let's go ahead and take a packet capture on mirror 0 port. We see that the ICMP echo replies are indeed getting hashed to VTEP2A. Earlier, we saw that VTEP2A was only learning one MAC address. It was not learning 4A89, that is host 1's MAC. Let's confirm that again by running show MAC address table. We see that there is no MAC learned. This means that VTEP2A is now going to flood this traffic to all the ports in VLAN 10 except for port channel 1 as the traffic was received on it. We will now focus on interface VxLAN 1 and port channel 1000, which is the peer link towards VTEP2B. Starting with interface VxLAN 1, let's check the flood list to see what VTEPs this traffic would be flooded out to. We don't see a flood list present on VTEP2A, even though the flood list source is correctly configured as EVPN. We can also run the command show VxLAN VTEP to see if any traffic is actively getting encapsulated on VTEP2A. We don't see any entry. Comparing this with VTEP2B, which has both of its uplinks active towards the spines, we see that the flood list is correctly populated. For any traffic that is actually running through VTEP2B, we would see this output reflect even in show VxLAN VTEP. Now that the flood list is empty on VTEP2A, the next port that we have is the peer link, port channel 1000. We have configured a monitor session on VTEP2B in the receive direction of the peer link to see if the ICMP echo replies are received. Note that in production scenarios, the peer link might be carrying additional traffic as well, in which case we can assign an access list to the monitor session and even add a filter to the packet capture in the TCP dump command. We see that VTEP2B is receiving the ICMP echo replies. A copy of this would also be sent from VTEP2A to port channel 2, but that does not concern us as it is connected to host 4. Let's see what VTEP2B would do with this packet. Taking a look at the destination MAC address, which is host 1's MAC again, we see that the MAC is learned on VLAN 10 on interface VxLAN 1. We would expect that this traffic is now going to get encapsulated into VX1 and flooded out to both VTEP1 and VTEP3. Let's go ahead and take a look at the counters for the uplinks towards the spines. Taking a look at the counters for Ethernet 49/1 and 50/1, we will see if any traffic is getting encapsulated out. We do see some non-zero values here in different bins. So let's run this command in watch diff, and we look for a bin that does not have the counters incrementing. We can take 256 bytes and above, 512 bytes and above, and so on. Let's first send the traffic for a working flow. We know that host 1 to host 4 works fine. So we will send a traffic of around 260 bytes with a counter of 20 packets in a time interval of 200 milliseconds. With this traffic flowing, we see that the counters increment exactly by 20. So we know that this bin is incrementing. Let's go ahead and now run this for the non-working flow, that is host 2. We see that with the traffic flowing, none of the counters are incrementing for 256 byte bin. This could mean that the traffic is probably not getting encapsulated out. In production devices, this counter might not be helpful if there is heavy traffic in all the bins. So in such cases, specifically for the device VTEP2A and 2B, we have the command show VxLAN counters VNI that is supported on DCS 7050SX3, where we can take a look at the number of decap and encap bytes for a specific VNI. We can also segregate this traffic based on the number of packets that were encapped and decapped for both bump traffic and traffic that was dropped due to a certain reason. Note that this counter is not available by default, and we need to configure this on the device. The command here is hardware counter feature for both VNI decap and VNI encap. This is also supported on different platforms, and we link an article for that at the end of this session. We already see that the encap drop packets are a non-zero value. Let's go ahead and check if this counter is incrementing. We will run the command again in a watch diff and send exactly 20 packets for the non-working flow. With the command running and the ping running, we see that the drop packets increment exactly by 20. This confirms that the traffic is actually not getting encapsulated out of VTEP2B. Now, this is an expected behavior, as any traffic that is received on pure link will not be encapsulated to VXLAN. This is a VXLAN MLAG implementation that avoids both the MLAG peers sending the bump traffic to the remote VTEPs. If this is an expected behavior, the next question that comes to mind is there no way for this maintenance window to work successfully? Well, the answer for this lies behind the fact that this is a design issue. If VTEP2A had the means of encapsulating the traffic and sending it across to VX1, it would not depend on VTEP2B to perform the encapsulation. Let's go ahead and check why VTEP2A is not encapsulating the traffic. Taking a look at the routing table, we don't see any routing entries for the loopback 0 and loopback 1 IPs. This would potentially impact our BGP EVPN peering, and we can see that this is down. This explains why we did not have any control plane information for the MAC address table or the flood list. In fact, this is notified by the show BGP EVPN sanity detail as a warning whenever an EVPN session is not established. If only VTEP2A had the means to retain the routes to loopback 0 and loopback 1, the control plane information would not be lost via the BGP EVPN peering. To do so, we can configure an iBGP peering between VTEP2A and 2B on the MLAG VLAN. We have a config snippet that is saved in the flash of the device over here that we will go ahead and configure. Note that we are going to configure a route map that ensures that the routes from the MLAG peer are the least preferred ones. Then in the router BGP mode, we define the peer group, we assign the remote AS, and assign the IP as well. The configuration snippet is same on both VTEP2A and 2B, except for the IP address. Let's go ahead and first configure this on VTEP2A and then on VTEP2B. Once this is configured, we would expect our iBGP peering to be up. And once it is up, let's go ahead and take a look at the routing table on VTEP2A. Running show IP route, we see that the loopback 0 and loopback 1 IPs are populated here. Loopback 0 for spine is also reachable, so our BGP EVPN peering should come back up. We can see that we are already receiving prefixes from the spines. Let's go ahead and check if this has changed anything in our MAC address table and the flood list. We see that host 1's MAC address is now learned on VX1. This means that if a traffic gets hashed to VTEP2A, it is now going to get encapsulated. Any active traffic that is getting encapsulated can also be seen in show VXLAN VTEP. And the show interface VX1, of course, tells us the flood list that is populated here. With this, let's see if our ping is working fine from host 1 to host 2. We can see that the ping has recovered. Let's also quickly confirm if host 3 is able to reach host 4. We see that the ping to 10.4 is working fine as well. With that, to summarize, this is not an issue with the configuration of the device. Rather, this is more of a design issue. With VTEP2A losing the uplinks, there was no way for it to learn the loopback 0 and loopback 1 IPs, and hence our BGP EVPN peering was down. Once we established the iBGP peering between VTEP2A and 2B, the EVPN peering was back up, and VTEP2A was perfectly capable of encapsulating the traffic. So in terms of the design, there are 3 important BGP peerings. First, of course, is the BGP EVPN peering that is represented in blue here. That tells us how we are going to exchange the control plane information. Then next, we have the BGP peering between the uplinks that is used for connectivity between the VTEP IPs and BGP loopback IPs. Other than this, we also introduced the iBGP peering between the MLAG peers to prevent the loss of traffic if the routes are not received from the uplinks. In terms of the commands, we focused particularly on show VxLAN counters VNI that helped us confirm that VTEP 2B was not encapsulating the traffic received on the peer link. With this, let's go ahead and take a look at our problem statement 3. We again have VLAN 10 here mapped to a MAC VRF, and all the hosts are part of VLAN 10. We do have an application server that is running on host 1, and the customer has reported that all the remote hosts in the network are facing packet loss towards application server. The nature of the traffic impact, however, is intermittent. There are impact windows where either all the remote hosts lose traffic to host 1, but then there are other windows where only a subset of hosts fail to send traffic to host 1. We do have a sample flow where at the time of the impact, host 2 to host 1 may not fail every time, but host 4 to host 1 fails every time. With this information, let's go ahead and take a look at the sample flows. We see that host 4 to host 1 loses traffic, but host 2 is working fine. Then both recover, and then again, both lose traffic together. Either way, there is significant loss in the traffic from host 4 and host 2 towards host 1. Given that host 4 is losing the traffic in every window, let's start with troubleshooting the flow from host 4 towards the application server. We have a continuous ping running towards the application server, and we are now going to take a look at the MAC address table. We do see significant number of MAC moves for the host 1's MAC ending in 4889. Taking a look at the VxLAN address table, we see that currently we are learning this MAC from the correct VTEP, which is VTEP 1. While we can run the watchdiff command on the show MAC address table to take a look at the MAC moves, recall that in the very first webinar series, we talked about the event monitor feature that can be enabled on the device to keep a track of the historic events. Let's go ahead and run show event monitor MAC and filter it with the match MAC command, where we add 4889 as the MAC address. And we also mention the time with match time command. We see that in this output, the MAC has flapped a number of times between VxLAN 1 on VTEP 1 and the local port Ethernet 54/1. From the diagram, Ethernet 54/1 connects to host 3. The customer here performed a monitor session on the receive direction of Ethernet 54/1 by applying a MAC access list that permits traffic sourced from host 1's MAC. And what we saw was that there are rogue ARP replies received from host 3 with host 1's IP and MAC. Given that these packets are sent every few seconds, that explains why we are seeing continuous MAC moves. Now we know that within BGP EVPN, when there is a certain number of MAC moves in a time interval, the device is going to blacklist the MAC or suppress the MAC. Let's take a look at what happens when all the traffic is lost from host 4 to host 1. We see that the MAC gets blacklisted on VTEP 3. What this means is that VTEP 3 is not even going to install the correct MAC IP route it is receiving from VTEP 1. Taking a look at the historic events again, we can see that the MAC has been suppressed a number of times and recovered as well. This explains why the traffic gets recovered every few seconds. We can see that the BGP agent is suppressing the duplicate MAC based on number of MAC moves in the last 60 seconds, and it recovers every 15 seconds. This is possible because of the running configuration under the address family EVPN as part of router BGP. The host flap detection command defines the timeout period after which we would remove or clear the suppressed MAC. While this explains why host 4 is failing, let's see what happens to host 2 when VTEP 3 blacklists the MAC. We will run the watchdiff command on show BGP EVPN host flap, and we will wait for the MAC to get blacklisted. We see that as soon as the MAC gets blacklisted, host 2 is still running the traffic. This is because VTEP 2A is correctly learning host 1's MAC address behind VTEP 1. In fact, we can confirm this with show BGP EVPN route type MAC IP, and we see that it is received from VTEP 1. If host 2 is not failing because of VTEP 3 blacklisting the MAC, we need to wait for the particular window when all the remote hosts lose traffic towards the application server. When that happens, we'll take a look at the MAC address table on all the devices. At around 170 pings, host 2 and 4 both lose the traffic to host 1. Taking a look at the MAC address table, we see that VTEP 1A is learning the MAC correctly on port channel 1. VTEP 3 is pointing it towards the local port Ethernet 54/1, which again explains why host 4 is failing. VTEP 2A, on the other hand, is pointing it towards the VX1 interface. Let's go ahead and check if any VTEP is blacklisting the MAC. We see that VTEP 1A, which is originally learning the MAC, is blacklisting it. When this happens, it is not going to advertise the MAC IP route to the remote VTEPs. This way, when VTEP 3 receives any rogue ARP replies on Ethernet 54/1, it is going to learn the MAC locally. It is also going to advertise this to the remote VTEPs such as VTEP 2A and 2B, which would now point it towards VX1, but to the wrong VTEP, that is VTEP 3. This explains why all the traffic from the remote host would get impacted towards host 1. To summarize, BGP EVPN blacklists the MAC based on the number of MAC moves in a certain time interval. This can be cleared out manually or automatically using the expiry timeout option in the host flap detection command. But the nature of the impact or the loss depends upon where the MAC is getting blacklisted. Here, when VTEP 1A and 1B that originally learned the MAC address are blacklisting this MAC, it would not be advertised to the remote VTEPs, thus impacting reachability to the application server. Other than the usual show BGP EVPN commands, the show event monitor MAC command and show logging are particularly helpful to see the historic set of events in terms of MAC moves and blacklisting. With this, we'll talk about a few useful commands that we saw today in all the problem statements. We talked about the show BGP EVPN summary instance and detail command that tells us about the state of the BGP EVPN peerings and the routes that are received or generated on the device. A very helpful command that we have here is show BGP EVPN sanity detail that can quickly tell us about any warnings or configuration errors that can potentially fail the control plane or the data plane. We also had a look on the show L2RIB input command for both MAC address and flood sets to see if the routes were getting imported into the L2RIB. Most of these commands are part of the show tech support and show tech support extended EVPN, both of which can be collected using the send support bundle flash command as of EOS 4.29.4m. While there are different issues that can crop up in a BGP EVPN-VxLAN environment, there are a few checks that are important in both configuration as well as troubleshooting. From a configuration aspect, it is important to ensure that multi-agent mode is enabled on the devices. The BGP EVPN peering should also have the send community enabled. Within the MAC VRF, it is recommended to have unique RD values and also to check if the route targets are correctly configured within the import and export statements. For traffic between host A to host B behind two different VTEPs, if we see complete packet loss, then for the bridging traffic, we need to check if the ARP is resolved on the end host. If the ARP is not getting resolved, we need to check if the remote end is receiving the ARP request. It is important to take a note of the IMET routes and see if the flood lists are correctly populated on all the VTEPs. If the ARP is resolved, but the traffic is still not working fine, then we need to trace the MAC address learning, both locally and on the remote interface VxLAN 1. The show BGP EVPN route type MAC IP is essential part of this troubleshooting. If the nature of the impact or traffic loss is intermittent, it would be good to check if the MAC is getting suppressed or blacklisted, or it is continuously flapping over a longer period of time where it's not getting blacklisted. With this, we have linked together a few helpful articles for both EVPN troubleshooting and general log collection, VxLAN, and TCP dump. And with that, I'm going to hand it back to Divya.
Thank you, Meethu, for walking us through those presentations on the three different scenarios commonly seen. That was great information. As Meethu mentioned, there's a lot of good commands and a lot of articles as well. All of this, as stated earlier in the call, is made available to you on our Arista community page. And you can also explore our Arista community page for various different troubleshooting articles that are written by Arista TAC. So with this, to wrap up, the recordings will be posted on that page. Our next session, which will also focus on EVPN, is coming up on September 27th, and we will wrap up the sessions for 2023 in October. That will be the final session on EVPN. Also, as a reminder, if you are interested in any customized training for your operations teams, you can get in touch with us at tac-custom-training@arista.com. All of this material will be uploaded shortly, so feel free to share this, and we will hopefully see you again on September 27th. Thank you so much and have a great rest of the week. Thanks.